Decoupling and Self-normalization by Professor Victor de la Pena. Victor is a professor of statistics at Columbia University, and he's a fellow of Institute of Mathematical Statistics and a medallion lecturer. Victor has done pioneering work on self-normalized martingales and on decoupling, and he wrote 2 standard textbooks on these 2 topics which are widely used. In addition, Victor's work has been published in top venues such as Annals of Probability and Bulletin of American Mathematical Society. More recently, he wrote an invited paper on decoupling and self-normalization for machine learning, which was published in the notices of the American Mathematical Society. Today and in the next, in the series of lectures, in the series of 5 lectures, Victor is going to tell us about all his results on decoupling and self-normalized martingales. Victor is going to visit us for all of this week and next Monday. If any of you that haven't signed up yet, if you want to meet with him, feel free to sign up. You can either contact me or Shubha. So without further delay, Victor, the floor is yours.
Thank you, no problem. Well, thank you for inviting me, Siva. So, yes, so I'm going to talk about 2 topics, decoupling and self-normalization, which are connected. The last chapter on my book on decoupling is the beginning of the book on self-normalization. So that's that's interesting. So, okay. So I do 2 types of decoupling. One of them is complete decoupling, and the other is tangent decoupling. Complete decoupling is where you find bounds to replace sums of arbitrarily dependent variables by sums of independent variables with the same marginals as the original. I will explain. And then the other, tangent decoupling, you replace the variables by conditional independent variables. And both of them have their applications. The first, the complete decoupling, has found applications in optimization. And so at the end of this series, my student will come and talk about that application. Then the conditional independent decoupling has found applications in matrix completion. So the first paper on matrix completion by Candes and Recht used the main inequality to develop their theory. Okay, then self-normalization. So this allows you to treat situations where the processes are non-linear. Okay, so I will explain what that means. And there is a way, the main tool to do that is what we call pseudo-maximization, which allows you to treat variables as though if they were constants. And this will be clear as I go through. I will, in case some of you are not familiar with some of the typical inequalities that I use, I'm going to talk about martingales and about some inequalities that are necessary for what I will do. Okay, so the decoupling for decoupling and self-normalization constitute domains that have evolved in response to the imperative of expanding martingale techniques to encompass high-dimensional, infinite-dimensional, and intricate nonlinear dependent structures. So, in particular, the decoupling, tangent decoupling, was originated by a paper of Burkholder. Let me see. So by the paper of Burkholder, a result of Burkholder and McConnell, and in that result, they proved the first decoupling inequalities in a Banach space. And out of that, a theory evolved that is called, that's what typically people say is decoupling in probability, which is different from the complete decoupling. I worked on complete decoupling on my own, and there was a group of Polish mathematicians who were developing tangent decoupling, and I joined them. Okay, so decoupling is help address dependent variables by treating them akin to independent entities, and notably it offers a natural framework for constructing precise exponential inequalities tailored for self-normalized martingales. So, as I said, the last chapter of my decoupling book was the first results in self-normalization for martingales. So I'll show you how that is done. Now, for self-normalization, I will illustrate its power by providing a self-normalized extension of Kolmogorov's law of the iterated logarithm. You see here we have a sum of independent variables, and Sn is a sum of independent variables, and we divide by the square root of 2n sigma square log n, and this is equal to 1 almost surely. We extend this to the case of martingales, self-normalized. So in that case, we replace, so we are going to take the martingale, and at the bottom we have the sum of the squares of the martingale, okay? And the same result holds, the upper bound. So we show that that works. So it's self-normalized in the sense that the top and the bottom contain the same variables. Please feel free to ask me questions if something is not clear. Okay, so this is basically a course in inequalities. So there's a quote that attributed to Kolmogorov that says that behind every limit theorem there's an inequality. So that justifies spending an entire course on inequalities. Okay, the first type of decoupling that I will treat is complete decoupling. And the inspiration for this is the decoupling that linearity of expectations provides. And so let me explain. So suppose that we have a sequence of dependent variables, possibly dependent, arbitrarily dependent variables with finite mean. And there's a way of constructing a sequence of independent variables such that d sub I and y sub I have the same marginal distributions, denoted by d sub I has the same law as y sub I. Okay, because of that, the expected value of di is equal to the expected value of yi. Yes?
You can use the laser pointer. It's the red button. If you press the red button.
Oh, I didn't realize that. Okay. So they have the same expectation. Now, linearity of expectations allows me to take the expectation inside the sum. And then the expectation of di is equal to the expectation of yi. And so I can then replace this by yi. And then I take the expectation outside, and I end up with this. So the expectation of a sum of dependent variables is equal to the expectation of a sum of independent variables. Now maybe I should come here because I don't block people's view. So now, in complete decoupling, so the question that I asked myself is, what can one do to extend the result in the case that you take a different function than the linear function? Okay, so we work with functions of the sums, and for some general functions that are not linear. Okay. So the first complete decoupling inequality that I know of is a decoupling inequality of Hofting, where if you have a population which consists of n values, C1 up to Cn, for example, decks of cars, then, and we take D1 up to Dn, we let that denote a sample without replacement. So it's a sum of it's a sample with dependent variables, and we let Y1 up to Yn be a sample with replacement. Now, the sample with replacement has the property that the Yi's are IID. Well, the Yi's are independent, actually, and the Di is equal to Yi. So they are not necessarily IID, but they are independent, and they have the D sub i's have the same distribution as Y sub I. So Hofting in 1963 developed the following inequality. So the expected value of a sum of the sampling without replacement without replacement is bounded by the expected value of phi of a sum of sampling with replacement for every continuous convex function phi. So that was the beginning of complete decoupling. Now, in an early paper, I proposed the following inequalities. So suppose that we have a concave non-decreasing function on 0 infinity, such that phi of 0 is equal to 0, and these other conditions are satisfied. So the constant c here doesn't depend on anything, it's just a number. So we have, this is a sum of dependent variables. The assumption is that there's a missing assumption here, which is non-negative. So if you have concave function, non-negative is a necessary property. So the expected value of a function of a concave function of the sum of the dependent variables is less than or equal than the expected function of the sum of the independent variables times a constant. Then if you have a convex function that doesn't grow faster than a polynomial, like that satisfies the property that phi of cx is less than c to the alpha phi of x, then the inequality reverses. In this case, you don't need to assume that the variables are non-negative, but in this case, the variables are a martingale difference sequence. So I need to add those two assumptions. So here you see, you assume they are non-negative, and you can decouple up. And if you assume that they are martingale difference sequences, you can decouple down. When you have a convex function, okay, when you have a concave function. Now, the inequalities do not reverse. You can either have this or that. And Peter Hall, when he saw this, a famous statistician who died a few years ago, he said that this shows a weakness of measuring expectation, of using expectation as a measure of the central tendency of a sum, because you know, the inequality cannot be reversed, and it depends on whether you have a concave function or a convex function. Okay. Now, the other decoupling that I will discuss is a decoupling that was initiated by Burkholder, Donald Burkholder, and his student Terry McConnell, and it's we call it tangent decoupling. This will be obvious later on. Okay, and Burkholder was trying to extend the theory of martingales to the case of Banach spaces. And the first inequality for decoupling inequality for Banach spaces appears in his paper number 1. Now, for any sequence of variables that is adapted to an increasing sequence of sigma fields, okay, then one can construct a tangent sequence with respect to the sigma field of the variables, and we can get a decoupled sequence which is conditionally independent. So we start with an arbitrary sum, and we are going to, what we can do is we can construct a sum which is a sum of conditionally independent variables, so that you can then use results for independent variables to study your dependent variables. Okay, so here is how one can construct one. You know, there are many ways of constructing decoupled sequences, but I propose this way because I thought that the other approaches were a little bit obscure. So this is a very pictorial way of doing it. So let's assume that you can repeat the variables, the distribution. You can repeat them twice independently. So here we have D1 goes from D1 to D2. They are dependent, and so forth up to Dn. Now, if you repeat the process that gave you D1 twice independently, then you get Y1. Then if you go from D1 to okay, then D1 goes to D2 dependence. You use the same random mechanism that took you from D1 to D2 twice independently, and you get Y2. So you see what I have here is a sequence of dependent variables, and at the bottom I have a sequence of variables which have the same conditional distributions as the original ones. But because of the way the variables are constructed, if we fix the d's, if we condition on the d's, this is a sum of independent variables. So here's an illustration of how you do it in practice. So suppose that you have a box with balls, and you are going to be sampling with it, sampling from it. Now, the first ball that you take out, that's going to be Y1. Then you put it back, and then take another ball. That's going to be X1. You keep it outside. So X1 you just, or D1 is just taking the ball and keeping it outside. So the context of the box has changed. The next step is at the third step, you are going to pick up a ball, and then that's y1. Then you put it back and take another ball, and then you leave it out, keep it outside. So this is how you can do this experiment, okay, pictorially. And it guarantees that you have a sequence of conditional independent variables. Now, one of the inequalities that I introduced that has had some impact on the way things are done in decoupling is, okay, so I just told you how to construct it. What you do is you have a sequence of dependent variables, and you construct a sequence of conditional independent variables. And if you put here a G, which is any non-negative random variable adapted to the filtration of the D's, so then you can decouple it. So you can get that less than the expected value of G squared e to the 2 lambda summation of yi. Now this allows you, this random variable allows you to decouple with constraints. And that was, that's what was needed. You see, I was talking to Talagrand, and he asked me, so can you provide, he asked me, can you do it with some constraints? And so this is the result. This is what happened. If you let G equal to 1, one gets the decoupling inequality for the moment generating function. And these inequalities are sharp. Actually, if you let G equal to 1, it's easy to see that this expectation, in the case that you have two variables here, is going to be an equality because of the way the construction goes. Okay, so now let's talk about self-normalization. So as I said, the moment generating function decoupling inequality that I showed was used to obtain the first self-normalized inequality that I got. And so in self-normalization, we have a canonical assumption, and then we use pseudo-maximization to produce self-normalized inequalities. And self-normalized inequalities, just as an aside, are useful in the theory of martingales, as you will see as we proceed. Okay, self-normalized statistics. The first self-normalized statistic that I know of is work by Gosset, which worked under the pen name of student, and this is a statistic that everybody should know if they took an elementary statistics class. And this result was very important because for the first time one could test hypotheses. Okay, so his student statistic allowed statistical inference about the value of the mean of a Gaussian distribution without knowledge of the actual value of the variance. And provided that you have a random sample from the target population. So, Gauss used the Gaussian random variable, but in the theory that was developed at the time, you needed to assume that the distribution has a certain variance. And if you had a small sample, the problem was that your estimate of the variance could be very unstable. But with a student, he provided a tool to deal with that problem. And so the world of statistics changed. Now, Joe Dube, so he's one of the founders of martingale theory. And I was visiting him in Illinois, in Urbana-Champaign. I was visiting Burkholder, and I used to hike with Dube, go hiking with Dube. And he suggested the problem. I asked him, what's a really good problem to work on? You know, I was young and I was very eager to learn. So he said, well, there are results in harmonic analysis where you take the ratio of a harmonic function over a superharmonic functions. But there are no results in martingales, practically no results in martingales. So what I got from that, that's all he said. So what I got from that was, what about getting inequalities for the case of martingale over super martingale? And so he told me this long time ago, and the question remained in my mind. And when I developed the decoupling inequality, you know, an application of it is some self-normalized inequalities for martingales. Okay. So now let us look at the canonical assumption. Suppose that you have a pair of random variables, A and B, with B bigger than 0. Assume that this expectation is less than or equal than 1. So in several situations, this is useful. For example, for all lambda real, if it's true for all real lambda, for lambda non-negative, and for lambda in a range. Okay, so this assumption is valid in a wide array of scenarios involving discrete and continuous stochastic processes, in particular in the context of super martingales. So I'll show you, my colleague Karatsas and Shreve wrote a classical book in Brownian motion, and in their book they talk about continuous square integral martingales with m0 equal to 0, then e to the lambda mt minus lambda square times the quadratic variation of m over 2 is a super martingale. That means that the expectation of this is less than or equal than 1. Okay, so in this case you take A to be m and B to be B squared to be mt, the quadratic variation. Now, in this case, a martingale assumes that you have a moment. Okay? So then, applying the methods of decoupling, some methods derived from decoupling, I was able to obtain this super martingale without any moment assumptions. So suppose that you have a sequence of variables adapted to an increasing sequence of sigma fields, and the d sub i's are conditionally symmetric. Okay? So given the path, the distribution of di is given fi minus 1 is the same as the distribution of minus di given fi minus 1. Then this is a super martingale. So you have sum of di expected e to the lambda sum of the I minus lambda square sum of the I square over 2, this expectation is less than or equal than 1 for all lambda. A remark is that there is no integrability assumption. So it allows you to treat with Cauchy random variables, for example. And so you can get away from the assumption of martingales if you assume conditional symmetry. So you don't need integrability.
Sorry, can you go back?
Excuse me?
Yes.
Yes? Oh, go back.
I just wanted to see the previous slide.
The previous slide?
Yeah, the one. Okay,
So A would be the sum of the di's, and B squared is the sum of the di squares.
thank you.
Okay, so the canonical assumption is that that expectation is less than or equal than 1. Now, I just want to mention that this doesn't have to be lambda square b square. So this inequality is related to Gaussian bounds. But it could be a function of lambda and b square, in which case you can treat the situation for variables with infinite mean, some variables with infinite mean. And you can find that in my paper with TLI and Michael Klass, which I will give a citation to, that property is valid. Okay, so suppose you have this. If the global maximizer of lambda square b square over 2, which is the maximizer is lambda hat equal to a over b square. It's a quadratic function, so it's maximized at a over b square. So then if a over b square is dependent, then when you plug this in there, you have that the expected value of e to the a over 2b square is less than or equal than 1. And that is an ideal. And by Chebyshev inequality, you have a sub-Gaussian inequality, the self-normalized sub-Gaussian inequality. The problem is that this is not to be deterministic most of the time. So you need a tool to obtain inequality to this one when you have random variables. And so you want to be able to extract a maximum out of this result, out of this bound. And the method of doing that is what we call pseudo-maximization, which is related to the method of mixtures, but it goes a step beyond. Now, okay, so suppose that you have a random variable in a measurable set. So we construct a probability measure lambda with distribution function f and independent of a and b. By Fubini's, so remember this is a random, for this is a fixed lambda. We are integrating with respect to the density of the random variable lambda. So this expectation, okay, if you put here a density, this expectation by Fubini's theorem is going to be equal to the integral of expected e to the lambda a minus lambda square b square over 2. Okay? Then the density is outside, the density of lambda. Now, remember that we have the canonical assumption says that you have this expectation to be less than or equal than 1. So then when you integrate with, so I replace this by 1, and I have an upper bound when I integrate the density, because the integral of a density is 1. Now, so that induces a sub-Gaussian inequality. So remember, the ideal inequality, so suppose that we have A and B arbitrary, which satisfy the canonical assumption, then for all lambda in R, then we have the following inequality, which is a general sub-Gaussian inequality. So remember, ideally we could remove the expected value of B quantity square. Okay, that would be ideal, but there's a price to pay because you have random variables. And this is a price that can be paid, and you obtain an almost optimal result. Okay? So I'm going to prove this inequality, and then not right now, but in future lectures. And also I will prove an improvement of it. The first result is easier to follow, so I would like to show you that one first, and then show you a way of improving it. And that result has been used for large deviations of martingales, self-normalized martingales. Okay, so remember the Kolmogorov's LIL we started with? So Sn is the sum of the yi's, iid. Then the lim sup of Sn over 2n sigma square log n is equal to 1. And Kolmogorov said that behind every limit theorem there's an inequality. And so in order to extend this result to the case of self-normalized martingales, replacing the sigma square by the sum of the variances, the sum of the conditional variances, or the sum of the squares, then we use the previous result. We use, you can do it by using the canonical assumption. So the inequality that is needed to do this, to extend this to martingales, self-normalized martingales, is the canonical assumption. Okay, so suppose that e to the lambda at minus lambda square, this should be a square, b square over 2 is a super martingale with mean less than or equal than 1. Then on the set that the limit of bt square is equal to infinity, the limit of bt square is equal to infinity, then this inequality holds. This limit theorem result holds. So the lim sup of at over 2bt square log bt square is less than or equal than 1. This is for a very wide class of processes. I will give you examples of those. Well, I gave you one. For example, in the case of conditional symmetric variables, this inequality works. This limiting result works. And in the case of Brownian motion and martingales, it also works. So the case of conditional symmetric variables, the sum and the sum of the squares satisfy the canonical assumption. So if I take on the set where the limit of the d sub I square goes to infinity, then we have that the lim sup of this is less than or equal than 1. And this is a sharp extension of Kolmogorov's LIL without moment assumptions, which is valid for Cauchy centered variables. Now, I just want to mention something that is often overlooked. Any sequence of variables can be can become can be developed by using conditional symmetric variables, so that the inequality really works for symmetrized arbitrary variables. But they are symmetrized, so you have to deal with the symmetry. Okay, so now maybe I should ask you, how familiar are you with martingales? I don't want to bore you. Is there anybody that is not familiar with martingales? Yes, okay, so there are people not familiar, so that's okay. That's fair. That's why I asked. So I'm going to introduce a little martingales. So in a measurable space, omega f, a sequence of sigma algebras f1 up to fn, which is an increasing sequence of variables, is a filtration. So fn represents our knowledge at time n. It contains all events such that at time n it is possible to decide whether A occurred or not. As n increases, there will be more such events A. So therefore the family Fn represents our knowledge will become greater. Okay? Now what is a martingale? So suppose that we have a probability space, omega fp, and a sequence of variables m1 up to m2 up mn is called a martingale with respect to the filtration f1, f2, and so forth. If ms is integrable, you need to have integrability. And m1, m2 are adapted to f1, f2, and expected value of mn plus 1 given fn is either less than or equal or bigger than or equal for each n. So in this case you have sub-martingales and super-martingales depending on. So the concept of martingales has its origins in gambling. It describes a fair game of chance. Similarly, the notions of sub-martingale and super-martingale defined below are related to favorable and unfavorable games of chance. No, so if you have less than or equal, that's an unfavorable game of chance. If you have bigger than or equal, that's a favorable game of chance. And the same thing works for continuous time martingales, for a sequence of continuous time variables, satisfying the same assumption as in the case of discrete variables. Brownian motion is an example of this. So suppose that you have a mean corrected sum of IID variables. So suppose an example is we take x sub I independent variables with mean nu, and we let S0 equal to 0. For n bigger than 0, we let Sn to be the partial sums. Then Mn equal to Sn minus n nu is a martingale with respect to Fn, the information contained in x1 up to xn. If we now assume that x sub I is a Rademacher variable, then this process is called the symmetric random walk. So it goes up and down. Is there any question? Is that a good example of of a martingale? Okay, and the same thing happens with Wiener process, with Brownian motion. But I guess this is more specialized. I don't think I should spend some time on this. This also works for Brownian motion, let's say. You can go back to the slides and check under what conditions. So let's rudimentary probabilistic inequalities, including exponential inequalities, decoupling inequalities, So the first inequality is Markov's inequality. So you know that one. Are like the prerequisites for this course. Holder's inequality. A lot of these things are easy to prove once you know how to do it. So that's so imagine, so the way one works on these problems is one looks at an area and then one looks all around and see what problem you can solve. So then, you know, so then the idea is you're going fishing and you're going to take whatever fish is around. And if there are a lot of fish, then that's your inequality. Now, Jensen's inequality. So if we have an integral real random variable and phi is a convex function, then phi of the expected value of x is less than or equal than expected phi of x. And there's an exponential inequality that is very commonly used, which is Bernstein's inequality. In this case, you don't assume that the variables have okay, so you don't assume that the variables are bounded. You know, like Chernow's inequality assumes that the variables are bounded. In this case, you don't assume that, but you have a control over the kth moment of the variables based on the variance. Then for all x bigger than 0, the probability that the sum of x sub I bigger than x, less than or equal than 2, than e to the minus x squared over 2 vn squared plus cx. Okay? Where vn squared is the sum of the variances. Now, so with the decoupling inequality, one can extend this inequality to the case of self-normalization in a sharp way. Okay. Now, Hofding's inequality I already described, so I am not going to bore you with that. Doob, we spoke about Doob, so he had some martingale inequalities that we have extended to self-normalized inequalities. So his suggestion was really good. So whenever you are with someone that knows an area, ask them, are there any good questions? Because who knows, maybe you can solve them. And if you keep on asking people, eventually you will get one. Okay. So the probability that the maximum of a martingale bigger than t is less than or equal than 1 over t squared expected n squared. This is an extension of Kolmogorov's inequality. And then the expected maximum of mk to the p less than or equal than p over p minus 1 expected mn. And the next inequality is Burkholder-Gandhi inequality. So if you have a martingale and you want to estimate this expectation, the expected value of the maximum, then it is very hard to deal with sums of variables that can be negative or positive. But if they are positive, you can do a lot. So what they found, Burkholder, Davis, and Gandhi, was that you can estimate this expectation by taking the expectation of the sum of the squares. And that gives you a lot of leverage because this is of the same order of magnitude. I want to remark that this is of the same order of magnitude, but it doesn't give you the order of magnitude. But if you use complete decoupling, you can get the order of magnitude. This is one of the tools that I use to prove complete decoupling inequalities. Then if you take this is an extension. If you have Rademacher variables, then the expected value of the sum of epsilon by xi to the p to the 1 over p is bounded from below and from above by the sum of the squares, the square root of the sum of the squares. In this case, the x's are complex numbers. So this is Khinchin's inequality. So Burkholder was inspired by Khinchin's inequality to obtain his inequalities. And this inequality actually gives you the order of magnitude of this expectation, because it depends, the order of magnitude is actually based on the sum of the square root of the sum of the squares. Now, now I come to, what time is it, Siva?
5 minutes to 2.
Okay, good. Okay, so I still have more material, so we can go continue. Okay, now the K function. So I am a student of Michael Klass at Berkeley, and his work has influenced my work. I mean, I learned from him, and I've been working on the things that he did, using them. And so the K function is a function that allows you to get the order of magnitude of sums of independent variables, of functions of expectations of functions of sums of independent variables, extending what Khinchin did. So you no longer have Rademacher variables, you can take arbitrary independent variables. So the K function is defined as follows. Let's take this is the inverse of this function. So what you're doing, okay, so basically what you're doing, imagine, so you're taking g of x equal to x squared over the integral from 0 to little x, expected value of y, which is the random variable, indicator that y bigger than u du. Now, you can think of the K function as the moment generating function, because it extracts the information on the distribution of the variable. So it's another transform that allows you to treat independent variables. So, homework. You didn't know that you were getting homework. So, using this, verify the equivalent definition of the K function, which is the unique solution of this. So, K squared of x is equal to x expected y squared minimum y ky of x, which is equal to the x times the expected value of y squared times the indicator that y less than ky of little x plus x ky of x times the expected value of absolute value of y on the set where absolute value of y is bigger than kx. Now, so you can find the proof of this in a book that I cite this is my book on decoupling. So there, if you cannot do the homework, at least you can go and look for the book. So this is a tool that I'm going to use to prove the complete decoupling inequalities.
Can you give me a high-level idea of the K functions?
Excuse me?
What's the intuition behind the K functions?
I wish my phone was working now, so I could call Michael class. To me, it came out of the blue. I learned it and I was able to use it. But, you know, the intuition, if you want, we can call Michael class and he'll explain. Okay, so the K function satisfies these properties. So if you want to extend, so suppose that you have IID mean zero variables. Okay, then the expected value of the absolute value of yi is less than or equal than twice ky of n and bigger than or equal than 0.67 ky of n. So this gives you the exact order of magnitude of the L1 norm of the sum of independent mean zero variables. Yes?
Is there an absolute value, Miss? Oh, sorry.
Yes,
Okay.
it's an yeah.
It's an absolute.
Otherwise, it's just linearity of expectation. So,
Okay.
so he was dealing with extended linearity of expectation, and so there's another paper that allows you to take any sum of independent variables and a function of the sum, the expected value of a function of the sum. And there's a generalized K function, and you can get bounds of this type for expected. So if you have to bound the expected value of a function of a sum of independent variables, you can use the generalized K function. And Class did this. He was the first one on doing it. And you can find the citation in the slides. I will ask Siva to post the slides so that you can look at the citations. Okay, so the citations are here. Maybe you can take a break. Thank you. Okay, so now I'm going to introduce complete decoupling. Now, complete decoupling is the tool that is used for solving optimization problems of this economy of with loss functions that are dichotomous. Now, so I will explain what that means in a few minutes. Okay, so now, so let's see. So I already explained this. So you have arbitrary variables, d sub I, with first moment. A basic question is how large can the expected value of the sum be? Now, if we know the expectations of the variables, then this gives the answer, the linearity of expectation. And the natural question is, how large can the expected value of the sum of the A's be? For martingales, Burkholder, Davis-Gandy inequality gives you the answer for martingales, except that what he does is he replaces the sum by the sum of the squares, and that's a very useful tool. But that is not enough to know what the order of magnitude is. I actually asked Burkholder. I asked him, so do you know the order of magnitude of martingales? He said, no, I don't. Okay, good. So I had something new. Okay, so in complete decoupling, one compares expected value of a function of the sum of the i's to the expected value of a function of yi's for general functions. Okay, so the complete decoupling based on linearity of expectation is this. This is an equality. It's not an inequality. It's an equality. Okay, so let's see. How do we construct the yi's, the independent variables that you can use to decouple? Now, I want to point out that, I spoke about Michael class, his results. So his results are for sums of independent variables. He has the order of magnitude. And so with the decoupling inequalities that I do, complete decoupling, you can get an estimate of the order of magnitude of dependent variables because class did the other thing. Class dealt with those for sums of independent variables. Now, okay, so how can we construct the yi's? So suppose you have a sequence of arbitrary variables, arbitrarily dependent. You repeat the process that gave you the sequence n times independently. And you take the diagonal. Now, D1 super 1 has the same distribution as D1. D2 super 2 has the same distribution as D2, but D1 and D2 are independent. So you see, this is a construction of the sequence of independent variables. I showed you a graph of how to construct a decoupled sequence, complete decoupling, and this is the way, that was a little picture, and this is the picture for complete decoupling. Okay, so what you take is, you take yi to be d sub I super I. And then yi is a sequence of independent variables, independent copies of d sub I. Are there any questions? Yes.
Yeah, mathematically, I can understand you can define such a yi, but from the practical point of view, will such a yi provide a new insight for the property?
Okay. Well, the practical thing is, well, if you want to get the order of magnitude of a sum of dependent variables, okay, of a function of a sum of independent variables, then that's sort of like hopeless. Because for one thing, you do not know the distributions, or you do not know the dependent structure. So anything can go. So if you know the distributions, okay, you can use the decoupling inequality and then use classes, the k function, to get the order of magnitude. So if you're interested in getting the order of magnitude of a problem, you know, I have a paper where we were working with loss functions. So, you know, so like actuaries, they have information, marginal information of how much it will cost them to treat one fire, one earthquake, okay? so they have the marginals. The question is, how much will an incident cost, which is a sum of dependent events. So the fire will cost something, the earthquake will cost something, some destruction. And so if you want to find the expected value of a concave function of the variables, of the sum, since you do not have the dependent structure, you need to find a way to handle that. So the inequality that I will show you can be used to get an estimate of that expectation. And the constant on the inequality, you know what I showed you in the beginning was an inequality for concave functions, and the variables were non-negative, so that applies in this example. And that constant, the constant on the inequality, that's the price that you pay for having for the lack of knowledge, for not knowing what the variables are. And up to now, the best price that I can give you. So if you were an insurer and you want to insure a certain town against disasters, then since I don't have the dependent structure, I don't have, but by using the decoupling inequality, you can then say the constant that I have, the best constant that I have is E over E minus 1, which is about 1.5. So the price of dependence is 50%. You charge more. You either give me the the actual dependent structure, or you pay 50% more. So that's sort of like the idea. And I will give a reference to that paper at the end. Okay? And any other questions? So now, so if we have a sequence of independent variables with identical distributions characterized by the cumulative distribution function, f, and we are interested in how large can this sum be. Kinch's inequality gives us the result when you have weighted sum of Bernoulli variables or Rademachers. And then, so this is Kinch's inequality. So the order of magnitude of this expectation is the sum of the square of the entries. The sum of the square of the constants in Kinch's inequality. If we take, so in this case, we know that if x sub I is equal to 1 for all I, then the expected value of the sum of yi to the p is of the order of n to the p over 2. Now, Kinch's inequality, a lot of people spent years trying to find the price, trying to find the sharp constants for Kinch's inequality. You know, some people are crazy. But one of the things that people working on inequalities is finding the sharp constant. So I'm a little crazy. Okay. So anyways, for a general distribution f, we need to calculate the following integral. So it's a multiple integral of a sum of yi's to the p. The density of y1 up to density of yn. Now, maybe a computer can give you this, but I don't know how. I mean, how expensive would it be, talking about money, how expensive would it be to calculate this expectation? Sometimes, you know, you don't have enough money to do it. It's not an easy problem. But if you use the k function, you can get upper and lower bounds on the expectation. So remember, I gave you homework, but maybe not enough time to solve it. So I spoke about the k function, which is the inverse of x squared over the integral of the expected value of absolute value of y, indicator that absolute value of y bigger than u du. Now, you see, this transform, so you can think of it, what's happening is, you asked me for the intuition of the k function. I called Michael. And he told me, well, you know, the k function is filtering all the information on the distribution of y through this integral. So, that's the intuition. You know, he was able to create another transform, like the Laplace transform or the moment generating function, that gave him even more information. Well, the Laplace transform gives you, characterizes the distribution. In this case, you are not characterizing this distribution, but you characterize it up to constants. So if you did your homework, you checked that this is y squared can be written in this form.
Yeah, from my point of view, in statistics or probability, we often truncate the data is too extreme. That's understandable. I'm more concerned why doing the integrations from 0 to x, that part is the...
Oh, well, what happens is, depending on how large your sum is, that will, so you don't need, okay. I will explain later,
Sure.
okay? Remind me. If you don't remember, I won't. Okay, so the ky of y of x exists and is unique, since the function expected value of x y squared t squared minimum absolute value of yt is strictly decreasing and continuous. Okay, so here I am dividing by t expected value of y. So this function is strictly decreasing, and you can use it along with the k function to show that there exists a unique solution. Okay? Okay, so now I'm going to show you how you can use it to, so I'm going to show you the proof of how to obtain the bounds. So if the variables are independent, we can let k of yn be the unique positive number k solving this identity, because of the definition of the k function. Okay, the k in this case is the k function, and so you could call it k sub k of n. So what you're doing is you take the expected value of yi, square it, and minimum k yi. Now this function can be obtained using the marginal distributions. Okay? And it's the k function at n. Now you see, if you are for each n, you need more and more terms, the k function at higher levels, to get the approximation. Okay, so this can then be written as the sum I going from 1 up to n, expected yi square over k square, minimum absolute yi over k, equal to 1. So there's a unique solution because this is decreasing from 0 to infinity. Okay. So if the variables are id, this reduces to n expected y1 square times the absolute value of y1, ky1 of n, equal to ky1 square of n. So, okay, so then the inequality is the following inequality. The expected value of the sum I going from 1 up to n of yi less than or equal than twice ky of n, and bounded from below by 0.67 ky of n. And if you want to estimate the sum of n variables, you need to have access to the k function at n. So that's why when you integrate over lambda, there's a point. Okay, so you do not need to integrate over the entire distribution to get these bounds. You only need to integrate up to a point. Let me see. Okay, so you need to integrate up to the k function. Is that giving you the intuition? So you're if you want to bound the expectation of your variable, you integrate this expectation up to the k function. Okay? So if you want to estimate the expected value of the absolute value of the sum, then you only need to integrate about 2x, which is related to the k function. You know, it's a brain twister, but that is the idea. Okay? To formalize this, it would take a little time. So, okay. So this expectation is bounded by 0.67 ky of n and bounded from above by 2 ky of n. Now, I will provide you the upper bound when the variables are symmetric. It would take a long time for me to prove the general result. I will just show you an upper bound when the variables are symmetric. Okay. From 7, we have that expected, if I let y prime to be y, indicator that the absolute value of y bigger, less than or equal than k, and yi double prime equal to y, indicator absolute value of y bigger than k. Okay. From 7, we have that n times y prime square less than ky of n square, and n times y double prime less than ky of n. Let's see that is the case. Okay. You see, this is the k function at n, and this expectation when you truncate at the k function, the y1 when you truncate it, so this is the sum of two terms. One is the n times the expected value of y1 square, indicator that y1 square less than absolute value of y, ky of n, and so forth. So these two inequalities are satisfied because of the way you define the k function. Then I asked you if you need Jensen's inequality, so you will need it. Okay, so we can truncate the yi's at the k function. And this is for less than or equal than kn, and y bigger than k of n, it's y. Okay, then you can use the triangle inequality to take this expectation and bound this by the expected value of the absolute value of the yi's primes plus the expected value of the absolute value of the sum of yi double primes. Then you use Holder's inequality, another one that I asked you to study, and you come to this place. And here is the triangle inequality. Since these variables are symmetric, you can take the expectation, this is going to be exactly equal to this, because this becomes the sum of the yi squares plus another term, but that term vanishes. So these two are the same, and these two are the same. But this is ky of n. This is bounded by ky of n square. Since we have a square root, that gives me ky of n, and this is bounded by ky of n. So that's where you get the 2. Any questions? Now, if you want to extend this to the case of arbitrary independent variables, you are welcome to read Michael Klass's paper. That's a difficult paper to read. But this simple thing gives you the idea. You do truncations and...
It's neat because these two terms have same upper bound.
Excuse me? Yeah.
Yeah, it's neat. I think the result is very nice. Two terms.
So, yeah, at some point he told me that that's what he was. So you got the intuition. He wanted to bound, to find a bound so that they would be the same. Yeah, you got it. So that provided the optimal. So you're treating the both truncations the same. So beside the L1 norm, the bound can be extended to the expected value of phi of the sum of the yi's for phi convex with a generalized k function. So you can find the results in class or sections 2 and 3 of my book on decoupling. Okay, so now I'm going to show you how to decouple martingales. And there's an open problem here for those of you who like challenges. As I told you, there are some crazy people that spend their time getting sharp constants. So decoupling of martingales actually doesn't have the sharpest constant yet. And I'll show you the proof. So how large are the expected value of the absolute value of d sub I to the p, and the expected value of the maximum of the absolute value of d sub I to the p. Burkholder-Gandhi gives us this approximation. Okay, that's what I presented in the first part of the course. So if the martingale has independent increments, then you can use the k function and you get the order of magnitude. Okay? But if it doesn't have independent increments, then you need to do something about it. So here's a theorem. Consider a sequence d sub I of mean zero martingale differences, and y sub I are independent copies of d sub I. Then the expected value of the maximum of the absolute value of di less than or equal than a constant times the expected value of the absolute value of the sum of the yi's. So you can remove the maximum just to make it easier to grasp. So the expected value of the sum up to n of d sub I less than or equal than a constant times the expected value of the sum of y sub i's up to n, where y sub I are constructed the way I showed you, taking the diagonal. Here we are assuming that the variables are martingale differences. So, okay, now, this constant, I don't know what this value is, okay? And so I only show you this one. This is one side of the inequality. Now, so this is a convex function. If you want to get I gave an example of the insurance company, the price of independence, for concave functions. And in that case, believe it or not, the sharpest constant is known. And it was obtained by two Russian mathematicians one was working at Microsoft, the other one was working at Yahoo. And the guy in Microsoft, which is Makaryachev, they had a problem with the scheduling of computer servers. And there were a lot of intricacies, a lot of dependencies between the servers. So Makaryachev, who was at Microsoft, went to the head of the group, the head of the research group, who was Yuval Perez, and he asked him, how can I solve this problem, And he said, well, go read Victor's paper. Go read his book. And he used the case of non-negative variables. He found the bound, okay, for non-negative variables. He found two bounds, one for concave function, one for convex functions. And the bounds gave him a good approximation on the price of dealing with the dependence, okay, which the price is basically the Bell number, the expected value of a Poisson to the power of the function that you are trying to approximate. Okay, any question? Yes?
Are these inequalities also known for Markovian sums?
They are what?
Like if di is a Markov random variable instead of mean zero martingale difference, are these kind of inequalities known for that setting?
I don't know if they are known. That's a good open problem. Let me think. You can sometimes take Markov chains and use martingales to study them. So maybe you can use them in that case. But directly doing, that's one thing that I haven't seen. So I came here partly because of that, because Siba is an expert on that type of dependence. So I'll be happy to talk to you about this. That's why I came. Thank you. Okay, so in order to prove this result, the proof is very simple once you know it. So what we do is we notice that the k function for dependent variables is the same as the k function for independent variables. So if d1 up to dn is a sum of dependent is a set of dependent variables, and y1 up to yn is a subset of independent variables, then the k function k is the same, because these expectations depend only on the marginals. So remember, I showed you the linearity of expectations was a key tool. So Michael Class was able to use linearity of, I was able to use that fact to prove the inequality. So that was fortunate. So you can then study sums of dependent variables as if they were independent. Okay, is that clear? So then we go to my old friend Burkholder, and you have the expected value of the maximum of the sum of the i's. So I'm doing it only for the case of p equal to 1, but the general case follows the same pattern. So by Burkholder-Gandhi, I can replace the sum of the di's, this expectation, by the expectation of the square root of the sum of the di squares. Then I truncate at the k function of the y's, of the independent variables, which is the same as the k function of the d's. And here I am taking di prime square and di double prime square. So what's happening here is I split this into di plus di prime plus di double prime. But you can then, the di square is the sum of di prime square plus di double prime square. Because of the truncation, the summation gives you the same thing. Now, this is a concave function. This is a concave function, so this expectation is less than or equal than this, because the expectation of this is less than or equal than the expectation of both terms. Here, what I do is I first use the fact that expectation of the square root of a plus b is less than or equal than expected value of the square root of a plus the expected value of the square root of b. And then, so that's this part. That takes me to this part. When I take the square root here, I get this. And then what I do is I then take, so you have the sum of the di squares, and the function is concave, so I can take that as the sum of the absolute value of the absolute values because of the concavity. Now, then, as I told you, this is a very easy proof. You can use Jensen's inequality again, and to come from here to here, and then by definition of k function, this is bounded by the k function. So the decoupling really happens at this point. When you replace this by the k function, that's where the decoupling happens. So you truncate at the k function for the independent variables, which is the same as the k function of the dependent variables. And then, so this is also ky of n. So this is less than or equal than the square root of kdn squared to the 1/2 times plus plus k of dn, which is twice ck of dn. C is the constant of Burkholder. And that's equal to 2 ck of yn, which is bounded from below by classes inequality. That's the proof. So I graduated, you know, with a very easy thesis. All I needed to do was to learn what Michael class did. That was painful, but okay, let me see. And you see, this is a little bit more than what I had advertised. This decouples the maximum. And this is related to Levy's inequality. Levy's inequality tells you that the expected value of the maximum of a sum of independent mean zero variables is bounded by the expected value of this absolute value. If you have martingales, you have this inequality. So it would be important to know what C is to find out. I had a group of French probabilists working with me. I brought them to New York. We were trying to find the constant, but it was not easy. We couldn't succeed. So if you want to work on this, I'll be happy to share with you whatever I know. Now, sums of non-negative variables. Okay, so it turns out that any result for martingales can be transformed into a result for sums of non-negative variables. There's a trick. And the trick is, okay, so there's this inequality. You have non-negative variables, and you find the independence copies of the di's. Then there is a constant C such that this expectation is less than or equal than the C times the expected value of the square root of the yi's. And you can approximate by the k function. I'm going to show you, so I know how to do it for martingales. I showed you how to do it for martingales. Now I'm going to show you how to do it for non-negative variables when you take when you have the square root. What you do is you are going to look at martingale. So you take random variables, Rademacher, where the Rademacher variables are independent of the d sub i's and the y sub i's. Then mj is equal to the sum of the square root of di epsilon I is a martingale, because the epsilons I are independent of the d's. That needs to be checked. If you didn't know martingales, that's a lot of work. Now here is the proof going from non-negative variables to from martingales to non-negative variables. The expected value of the sum of the i's is equal to the expected value of the square root of di square times epsilon sub I square, because epsilon sub I square is equal to 1. Then, using Burkholder-Gandhi, you end up with this. You have this bound. These are di's. These are you take the when you take the square root of these, you end up with square root of di ei. Then you use the inequality for martingales that I showed you, and then you use Burkholder-Gandhi again. And that's the entire proof. And you know, the inequality also works in reverse for p powers p bigger than 1. Okay, so this is what I showed you before about my work. I have 30 seconds, so let me show you the main result. So after 30 years of working on my paper, okay, Makaryachev and Svyridenko, they came up with this result, and it was motivated by a computer science project. So if you have arbitrary dependent variables and the yi's are the di's are non-negative. So here we are assuming non-negative. Then the expected value of phi of p times the sum of the non-negative variables is bigger than or equal than expected phi of the sum of yi's, where p is an independent Poisson random variable, independent of the d's, okay? And therefore, if I take p to be equal to, if I take at the case of p is equal to bigger than or equal than 1, then I can take the Poisson out, expected value of the Poisson to the p, and I get this inequality. So this is Makaryachev and Svyridenko's inequality. They did it in a completely different way. They really had to work hard. So okay, and here are the references. So, and it's time to go. Thank you. Any questions? Yes.